You're good. Okay, good morning, everyone. Good morning, Zoom audience and in-person audience. So it's a great pleasure to welcome back Raimar Wulkenhaar, who will be in the third and maybe the last
maybe
installment of this series on how topological recursion helps with quantum field theory and non-commutative spaces.
All right, thanks a lot. So it works everything. Okay, yesterday we arrived at this point. So we have such a Dyson-Schwinger equation for our cumulants of this quartically deformed Gaussian measure. The EKs parameterize the Gaussian measure. Lambda is a factor in front of the deformation. And I should, it's not included here. So there is a factor 1 over script n, which is not the size of the matrices, but this is the scale of non-commutativity. Good. So Alex showed how most terms arise, and then there is something else, all this garbage. And this is put here. And this t is in fact, so it's the derivative of our two-point function with respect to these parameters k, and then we extend it to recognize, well, this is a function then of some complex variable, and set this variable to ek, then this gives the derivative. All right, and then I told you, well, we have this formal 1 over n expansion, which will not converge, but anyway, let's do this. And then we plug in these, these expansions into the previous formulae, and then you order in powers of 1 over script n, or script n square. But you declare that here, this 1 over n in front of the summation is neutral, does not go to higher genus. This will make sense, and we will show it. Okay, so this was what we arrived yesterday, and then in particular at lowest order, so genus 0, we get such a closed equation only for this planar two-point function. So, and today we want to solve it. So, and solve means this equation will have a problem. It's the usual problem of quantum field theory. The sum is unrestricted, so over all natural numbers, and this creates problems. So these sums will not make any sense. So today we will restrict them to some finite cutoff, and then we have to do something that I explained on the next slide. Good. So here's what we do. Well, we restrict the sum to a multiple of our scale. Multiple is lambda square, and lambda square at the end should be sent to infinity. But to do it properly, we have to do something. So we derived previously that our EK, so these pairwise independent values of these capital EK, they come with the factor tilde m square, but tilde there is previously we had the +1 here, and I absorbed it. Okay, and now we have to, well, this is the sort of mass of quantum field theory, and this mass is not observable. So that's an experiment. If you then zoom into your particle, you see that the mass is not what you think, the mass changes. In fact, well, this diverges. So this real bare mass is infinite or minus infinite. And well, we have to use this. So, okay, let's make this a function of our cutoff lambda, and also rescale our two-point function by factor. And the aim is now to find the function dependence of here and there, such that in the end we can go to the limit and everything exists. So, okay, making all these changes, and well, we have to throw out this tilde m. So we shift our variables so m comes here, and everything else cancels, and then we redefine our g's. And I omit the tilde to make it simplify. So the previous equation is just the same, but we move this m square here because that's what we have to determine. So, and then only this first term of the case is then indicated. Well, okay, that's what comes out. So this is a result in 4 dimension. In 2 dimension, there's no square root. So that's the difference. Good. So, and then you see, well, this is an approximation to an integral equation.
Yeah. Here in 2 dimension, you can also mention that z of lambda is not necessary.
This will come.
Okay, sorry.
Yes, of course. Good. So, okay, it's an this integral equation. If you approximate these integrals by Riemann sums, you end up exactly here. So, and conversely, you know, if this n script n is large enough, then there's only an epsilon difference between the 2 equations. So therefore, let's start here with integral equation, because then we have tools from complex analysis.
So sorry. So the unknown in the integral equation.
No, sorry. This is just here a scale factor which you also don't know. This is not the partition function.
It's the field renormalization.
Yes.
Quantum field theory, field renormalization.
It's also called Z.
It's not.
Oh, it's not a partition.
Yeah.
No, sorry. Good that you asked. No, it's important. Partition function I ignored by calligraphic Z.
Oh, okay, right.
And this is so-called wave function normalization, which in physics is also called Z.
Okay. So this is.
It's a factor which we have to find.
So it's just a number or is it a function?
It's a function here for space reasons. It's a function of lambda.
So it's a function of one.
And also this m is a function of lambda. Well, to make it in one line,
So is it like one real or complex?
so we have here a lambda, and we have m is depending on lambda, and all these z, well, they're the same. They depend on lambda, and we have to find this function relation.
G0 is just the uninteract in
No, it's the complete
propagator.
planar, no, not the propagator. It's the complete all Feynman ribbon graphs which are planar added up.
Oh, the plane.
That's the planar part.
And they are renormalized.
And yeah, this is a requirement. The limit lambda to infinity of these g's exists. That's the game. It's the usual game of renormalization quantum field theory. The point is that here, usually you do it graph by graph in perturbation theory, and here we do it globally in one equation.
So you got off. See
Yes.
what happened in some sense. So
Exactly.
Some sort of this scaling game.
Sure. Sure.
This renormalization is really like scale,
Sure. Yeah.
which is fundamental.
Yeah. Well, this is the idea of Wilson. You have scales, and everything is scale dependent. You have a flow of effective actions, and so on. So this is behind here.
Thank you very much.
And in the case where the lambda goes to infinity, this mass goes also to the mass.
Well,
also
minus
to
infinity, in fact.
What?
Minus
Oh,
infinity.
minus infinity, sorry.
Great.
Oh, wow. And then you have to rescale that too.
I mean, otherwise this equation would not
Yeah.
make sense.
Oh, I
It's
see.
support.
Yeah, yeah.
And also the wave function normalization, so it also goes to infinity. Or minus infinity,
Or maybe to zero.
maybe to zero.
I think to
Yeah,
zero.
it's-
So there's zero and infinity, which is okay, dual each other. Yeah.
It's like ultraviolet and
No,
it's not that.
depends on the definition whether you put the z or 1 over z.
Zero and infinity, the difference is okay.
No, this is the same. It's just convention that here we put z or instead of 1 over z. Okay, so that's the challenge. Okay, we had this equation in 2009, and it took us almost 10 years to solve it. And well, okay, now here's we can just remark, we can put a whole list of models into this equation. We only have to say what is this measure. So Previous slide, we had measure as t times characteristic function on 0 lambda square. Then this is the 4-dimensional case. In 2-dimension, we have no t. There are no multiplicities of the spectral values, just the characteristic function. And then we can put z equal to 1, was the remark for Alex. Or we can also do finite matrices. This is now a true n, the size of n times n matrices. And then this model can be put also in this integral formulation where we have this sum of Dirac terms in measure. So all this can be formed in the integral equation, and I will just sketch. There is one solution which captures everything. So okay, there's one important thing. Everything depends on the spectral dimension in the sense of noncommutative geometry. So here the measure, so these somehow tell us how fast the eigenvalues of the Laplace operator or the harmonic oscillator Hamiltonian grow with the cutoff. So, and this encodes, this is Raimar theorem, which gives the dimension from the spectrum. And this is the same as here. So your geometry, it's a geometry, not on topology, encodes dynamics, and we have a dimension, and this is here encoded in, well, in the spectral measure. It's not surprising. So, and then, okay, we see that, well, this is the same. So here delta is really 4 in case of 4-dimensional Moyal. Here it's 2. And finite matrix is a little bit special because the role of n is different, but can be understood as a 0-dimensional model. So, okay, well, the totally simple but important step was, well, study what happens for ρ equal to 1. And then, okay, there's a natural ansatz which follows from theory of linear singular integral equations. We do this, and it comes on the next slide. And then we get other equations which we solved perturbatively. So I managed to do the first terms, and then with the help of Erik Panzer, so specialist on iterated integrals and theta values and so on, he has put it on a computer, and overnight he came to order 10. So I was maybe 3 or 4, but terms increased enormously. And then we saw that the coefficients are special. They are Stirling numbers. And then, you know, the series of Stirling numbers then come to a conjecture, which we prove and so on. So this was the way. And then here, okay, then we generalize same more.
But I mean, physically, Raimar, rho 0.
It's just.
Density is constant.
No, well, this is the multiplicity.
Okay.
So you have equally spaced eigenvalues here, and they come with multiplicity. And if the multiplicity is 1, you are in 2 dimensions. If it's k, then it's 4, or k squared, then it's 6, and so on. Good. Okay, so that's the ansatz which is standard for linear equations. Always do this. Okay, let's do it. Then everything is expressed in terms of an unknown function tau. And okay, let's suppose tau is the imaginary part of a logarithm at the cut of, okay, one function depends as trivial, and the other one is such a okay, strange relation. You have another function RD, which we don't know yet, and then, okay, make this ansatz. But this came out of our solution with Erik, and then, so Alex told me, well, such a thing, or the relation here is which appears in topological recursion. And then I know this is the right ansatz. Good. So, okay, we have expressed G, which we don't know, in terms of two other unknowns, namely tau and RD. So RD is, well, this is the generalization of the method here, as given by such a formula, depends on the spectral dimension, but it involves another function, rho lambda, which is not the same as rho naught. So now we close everything we guess, or whatever. Rho lambda is the solution of this equation. So rho naught of RD of theta is rho lambda of theta. So the miracle, well, okay, just, okay. Doesn't mean anything that this has something to do with the solution. But the miracle is, well, this then proof is similar what we did then with Eric. You do all this, plug in, so all this definition into G, then insert into this equation, and it's just, it's an identity. Okay. It's exactly solvable for a reason which you don't understand. So this, okay, this falls from heaven. Okay, it just works.
I mean, the solution is highly implicitly defined.
Sure.
It's very complicated.
You need to do Lambert.
I mean, R depends on rho lambda, but rho 0 of R is equal to rho lambda. So these two red equations, they're completely implicit.
Yeah.
Fine.
Define RD.
RD is defined as upper
RD
equation.
is here.
Depending on rho lambda. Rho lambda depends on R.
So, okay, this system somehow you have to solve, and then you have RD, you get I, you get tau, and then you get G. And the miracle is it just works. It's an identity then doing all this. And the proof I also like because it uses very old mathematics, basically of the 18th century. So therefore, I like it. So in case if rho lambda is 1, so then R2 is Z, I think plus lambda log of 1 plus Z, if M is 1. And then you need here the inverse, and the inverse is given by the Lambert function. So then that's the solution, and you plug it in, and everything works in 2 dimensions. So we came to this solution here by guessing a perturbation series. The Stirling numbers, they encode logarithms and so on.
This Lambert W has branches, so
yes. Okay, this is a principal branch here. You see.
So
you're
this
right.
Is the only conversion.
Sure. Right. There are a certain domain of lambda in complex plane where this is well defined. You are completely right.
Other branches are also.
They are important. Well, when you discuss everything, there are certain, well, to get the domains, and so there are nice curves. Something which was used in by the Greeks to trisect an angle. Such a function appears there.
Oh, yeah. Also say something. So the perturbative expansion is at lambda equals 0. Look at the solution. It's all the time terms with 1 over lambda and exponential of 1 over lambda. So the perturbative expansion is lambda equals 0. So it's complicated to guess the solution. I mean, it's like a instanton.
Yeah. Exponential 1 over lambda is instantonic always.
Yeah.
So it's a resurgence.
Yeah, there's something, I'm sure. Well, this is really the exact perturbative solution, and just as you remarked, there is resurgence in the perturbation series somehow. Sure. Good. So let's do 4 dimensions. Interesting case. Then this equation here, so D is 4, you get the Z square in front of it to get this equation, which we have to solve. And now there's a very important discussion. Okay, suppose rho lambda is, okay, that's the definition, yeah. Suppose rho lambda behaves asymptotically in the same way as rho naught. proportional to t. Then you see, well, this this x square factor wins. So you cannot use t plus x here to go here to 1 because this diverges. So you can only use the factor 1 minus epsilon here. Otherwise, it's okay. You have to keep an epsilon here. And the other one compensates here. And then you see, well, if x goes large, this second term wins and the function goes down. So it has a, well, has a maximum, or well, maximum, yeah, it's indeed. So it's bound above. And this means that the inverse, which we need here, does not exist globally. So this is exactly a formulation of the triviality problem. We cannot go to infinite energies. So this is what you think. And we really thought, well, this will be the case, and that's the end. But things are nice. It turns out, well, you can solve this equation. There are various techniques by summation of integrals. The nice things, you get so-called hyperlogarithm in 2 letters, 0 and -1. And even Riemann zeta values. And the strange thing is the even Riemann zeta values, they combine to the arcsine function. So what you end up is that R4 or rho is the Gauss hypergeometric function. And the dependence on the coupling constant lambda is inside the parameters of the Gauss function in such a absolutely strange manner. Inside the arcsine. Now, if you perturbatively expand it, that's a horrible expression. So in X, you can easily expand. But in the parameters, this is a horrible thing. And this gives all the richness of quantum field theory. It's captured in the globally extremely simple function. But expanding is it's horrible. So the main thing is now that now we have a global solution. This exists for all x positive, what we are interested in. And you know the effective behavior of the Gauss function. And from that, we insert here now rho lambda to get an effective spectral dimension. And this effectively reduces dimension to 4 minus twice arcsine lambda pi over pi. So this was completely unexpected. That so the free theory, as we knew, has this well, it's dimension 4, but in commutative geometry, you get this triviality problem that you cannot put in interaction because things okay, there's a mismatch, and here, effectively, due to the interaction, the effective dimension goes down, and if we are less than 4. The theory is non-trivial. So therefore, at least in planar sector, everything works.
Sorry, the Eisenman result, 4 minus epsilon.
There are 2 results. In 4 plus epsilon is trivial. This was known in the 80s. And now, very recently, 3 years ago, 2.5, it's also in 4 trivial.
Oh, so they went down. 4 minus epsilon was okay.
But 4 minus epsilon is okay, right?
4 minus epsilon was okay. It was always okay.
So it's 4 plus epsilon.
The so-called Wilson-Fisher fixed point, which appears there, and then it's okay.
So now you are also effective dimension of your space. 4 minus epsilon.
And epsilon is very precise.
Okay, because
yes, of course. Yeah, we cannot make this link yet because the challenge is, so I brought here in planar sector. So we have to do with this. We have to understand all the non-planar sectors and we'll make sense of this well-Borel resummation in order to get the full 2-point function. This is not yet down. So we have to understand the higher topologies. And there, topological recursion enters. So I hope I have time to tell you this. Good. So one remark, so I edited the slide because Alex included it yesterday. So, well, this is the bijection of our terms of higher endpoint function with nested Catalan structures. So you have, well, these chord diagrams, there are Catalan many chords, different chords, and inside every pocket we have rooted plane trees, which are also counted by Catalan. And the main thing is there is a bijection between the blue and orange trees. If you know one, you know the other. So therefore, there is only this. Well, okay, there are that many of them. And so the rule is this green chord stands for two-point function. And every edge, they come with the orientation. And there's always a root. There's a nature orientation, and the first chord gives the root. And then this gives here downstairs this vector. And okay, you can then easily understand which terms appear. Just this remark because Alex mentioned it yesterday. And there's connection to Catalan, which we have seen many times. Okay, so let's do something else. So we want to study the higher topology sectors. And to do this, it's better to go back to true matrix models, n by n matrices, Hermitian. So, and so previously, we had more or less this inner product on our vector space, which then gave the Gaussian field. So we had here 1 over script n, and it was an infinite sum. Now suppose we have a finite sum and the script n, so they are the same. So let's do just an exercise. Let's do this. So important remark is, well, okay, this is all right. And now we deform this measure, and we well, we could add the phi cube term as a deformation. These are true traces. They're no longer distributions. And then, well, this is exactly the Kontsevich model, which proved the conjecture by Witten that there is a way to encode intersection numbers of psi and kappa class on the moduli space of stable complex curves. Okay. I will not tell you this. This is maybe this. It's absolutely the key example of topological recursion. If you take a spectral curve x is z square, y is its thing, Bergman kernel for omega 0, 2, and you run the topological recursion, then essentially the moments of this measure properly rescaled give the omega gn, which come from topological recursion with this data. So there's a technical thing. Okay, there's E hat, and you have to. This again, it's an implicit behavior, as we had previously. You have to implicitly find your C from this implicit equation. This deforms your spectral values. This is the analog of our R. They're real parallels. And then, well, that's it. Can be found in our book. So the remark is, well, this Kontsevich model, we can also here go to infinity here or script n and do everything on Moyal space, realization, everything works. Everything started. But the remark is this is not a valid measure because this I here produces signs. So it's plus minus 1. So it goes negative, it's not a measure. If we go away, take here real one, then it's not bounded below, and it also does not exist. So this makes only sense in formal measures, okay, perturbatively. So therefore, we are interested in the quartic case, and that's okay. What we
is conditionally convergent, but like
well, with the I, everything converges, but then we go negative. So it's a signed measure. Okay, so let's put here instead of phi cube, we put phi to the 4. Because that's the natural extension of what we did previously. So remark is, okay, let's call it quadratic model, but this should not be confused. I think this also on Alex's exercise slide yesterday, that there is another family of so-called generalized conservation models which relate to R-spin intersection numbers due to Elva, Inhar, and the young collaborators. Absolutely nice model, but this is different. So and the other remark is you can do everything for complex matrices. And there's a paper by Alex and Johannes Branal, my PhD student, 3 weeks ago or so, that this gives then something which obeys topological recursion. Read the paper, nice work. Whereas the real model is much more complicated. So I discuss here the real model, where we come to blobbed topological recursion. And the points where, where the blobs appear, this is done in the paper. All right, so let's go back. So this was our previous equation for what the 2-point function, now specified here. This is straight n by n matrices, and we have d many different little EKs, and Rk is the multiplicity, and the sum of the Rk's is n. So that's the situation. So now let's do the same thing as we did first. This is the magic equation. Okay, so I did this with my colleague Jörg Schirmann. Suppose we have some function R of degree d+1, simple port infinity residual -1. Okay, just sitting, and there is such a magic relation. This comes from essentially here. This is the red part. And if you plug in zeta is R of z, then you get here the left-hand side. And suppose this is minus R of minus z. Suppose, let's do it. So then you end up here in the linear equation, and there are theories, effects are simple to solve it. So you express, okay, one remark, also we do this change of variables. So previously we had G naught of psi eta and the script G of ZW, and this and the inverse of the transformation. Okay, and in the fiber of the EKs, we choose some epsilon k. So, okay, then we end up with this equation, a linear equation, more or less easy if you know what to do to solve. And then we express G in terms of R. So now you have to check that this equation is satisfied, and it's the same miracle, it's just true. So, okay, this is one fact, it's true, and you get for free what R is. This is essentially what we had previously, just comes out from this Ansatz. And we understand, so here we know from all these steps, we know what tau is, but then we have here to, again, this Hilbert's transform, find Hilbert transform to do. So G in general is only given by complicated integral representation. But in this final dimension case, it's easy and we can give an explicit formula. So, okay, it's a ratio, and here we need, if you go back to the original variables, we have to invert it. So here you need R inverse at these steps as before. And the numerator depends only on R of W. Here's the formula. So it's a product over all points in the fiber of W and R. And remarkably, that's a symmetric function, which you will not guess. Good. Okay, so that's this finishes the 2-point function, and now okay, let's go to higher genus. Good. All right. So remember, this was our equation which I showed you this morning in the very beginning, which we derived or Alex derived yesterday with these techniques, basis motion and Ward-Takahashi identity. So and then so all this garbage we collected into this t, and t was the derivative of the two-point function with respect to the e's, and then complexified. Okay, now we do this one over n expansion, so then we have this term which is next. So we have to know it. And it's now more or less clear what you do. You differentiate this equation once more. And then you get at next order an equation, so differentiate with respect to EC, whatever. This G is then by differentiation turned into a T. And then here's another differentiation, and you call it another T. What you don't know, you call it another variable, and this is 1 over n suppressed. So we don't care, you get again equation then for this t, and you continue this business. So remark, there is one thing which is okay, especially fascinating, I would say. We've seen yesterday this combination appearing in Alex derivation. So let's call this an omega 1. Let's do it. And then if we differentiate again and again, this produces then higher derivatives, which we call then iteratively go from omega n to omega n plus 1. And then differentiating, we get here from these terms a special term, which is only there in, you can only differentiate it once. We put this into omega 2. It's also standard redefinition. So then you get a bunch of equations. So here, this equation for these t's, and there are 2 of them. I have not shown you before the equation for this function with 2 cycles of length 1 will come, which we also treat with the same method. And then, so we have equations or coupled system of equations for these 3 objects, and then we genus expand and so on. And so I show you these equations, but so they are horrible. It's completely straightforward to derive them. Okay, I show you here. And then the aim is, well, solve them. Good. So again, remark, well, this thing introduces these straight t's tilde omegas, and then we do this change of variables, which we did previously from our straight g to script g, and we do here the same. So then, it's completely straightforward from this equation to and all these redefinitions to end up here. Well, okay, that's an equation, and then you can do the same for the equation for this other 1 plus 1 point function. So 2 cycles of here, this is 2 cycles of, no, 1 cycle of length 2 in permutation, and then we have the trivial case 2 cycles of length 1, and this gives the equation here. So everything is covered. So you see here is this 2 cycles of length 1 appears here. It contributes to higher genus, whereas the other one is neutral. We need the omegas, and then, okay, they're also here. And there's then an even more complicated equation for the omegas. Don't try to understand this. It's completely straightforward, and they are horrible. Pardon? Well, do you like this?
People like calculation.
Yeah, okay. So, okay, but the surprising thing is the solution of this system is so simple, at least relatively simple, much simpler than you would expect. So let's start with simplest case. So G is 0, and so I is then the length is other parameters. Just for I put another, I think U I will call it. So one variable, equation for omega 0, 2. Then everything collapses because here you see here there are these conditions, and in this case, so this goes away, this we have. Here, genus reduced by 1 does not exist, so these terms go away. There's all, okay, this we have, and this does not. That's two point, okay, that's two point function, yeah, good. So, okay, we end up with a relatively simple equation. And now, well, this is coupled. So, okay, then you think you need also an equation for the first of these t's. And if you look at the equation, this needs an omega 0,2. And then you think, okay, I don't know what to do. But the remarkable thing is that the poles separate. So we have this partial fraction decomposition of the two-point function, which we knew from our previous result. And okay, I should go back. I should say what this gotic G is. So G, this gotic G is the residue of our two-point function at the opposite diagonal, where we have a pole, simple pole, and the residue is this gotic G. And this appears here in front on the left-hand side. Good. So, well, here it is. That's the residue, okay. And then there are the other poles we also know. These are in the other pre-images point in the fiber of epsilons. There are d many of them. Okay, so we have this decomposition, so you plug it in, and then the poles separate. So these poles from here, they must combine with this thing. Okay, here, insert this here. And this term just must then give the poles of omega 0,2. And therefore, you just conclude, well, omega 0,2 is very simple. It's essentially, okay, this is a triple prefactor always, which if you go to little omegas, next step, we multiply through, and then we have here the Bergman kernel of topological recursion. So, and then there's another piece. Well, this is a blob. But that it's so simple, it's a complicated system gives such a simple answer, and of course, then we started, okay, now everything is all right. Because before, remember, we introduced, so we called this omega, omega 1, and then differentiate again, we had omega 2 with this prefactor, and that this is the right thing which relates to topological recursion you would not expect. But it is the right thing, and it gives, well, we have omega 0,2. So then you continue, well, first really by hand was not really fun. And we got omega 0,3 and omega 1,1. And then, okay, so I did this, and then Alex and Johannes understood that we know parts of it. Namely, the blue terms, except here in the plus and so on, they are familiar. They appear in our book or whatever. So they are standard for topological recursion. And then there's something else, term in red. Well, they are what they are. Okay. And then, so it means the blue terms, they are really produced by the universal formula with the current compensation. I'll show you one of the next slides of topological recursion. And then you add something else. And the something else is not completely free. Well, we get it. And luckily, there was an available theory due to Gaëtan Bourreau and Sergei Shadrin, who exactly did this. They extended topological recursion for a very natural reason, which I will also explain. Well, these red terms, they are just the blobs in the sense of Bourreau and Shadrin. Okay, so this made us happy, but of course, well, we had only the first highest, where you count Euler characteristics. But, well, you have then, there's all this equality of rational numbers, so it's more or less natural to expect that this pattern will continue. And well, I should say we have a proof for genus 0, but not yet for higher genus. That's work in progress. And I will tell you what we did to prove it. So, so we noticed, well, okay, we tried to work it out, and then we noticed that there is, in this particular case, absolute Hessian interplay between the omega 0 m's. Okay, you always distinguish one variable, and if you reflect z to minus z, then there are default relations. And we understood them more or less, what they mean. And the relation which we found or conjectured and then proved is this. It's here, it's formulated in a more general case. So, but okay, let me make this remark. Alex then understood that this can be vastly generalized. And this led to his paper on the XY symmetry and the talk on Monday. The origin is this relation which we had here. And this reflection z to minus z, well, this is what is here. So the x of topological recursion is r of z, and the y of topological recursion is minus r of minus z, which we have seen all the way previously. Starting here, this is the y. So in this reflection, then, okay, Alex understood that this is more general. It's the XY symmetry. Good. So, okay, let's do the following. Suppose we have the situation that x and y are related by such an involution. Suppose that's the case. So, and the omega 0,2 is symmetric under this involution, and the higher omegas, they satisfy such a formula. So the reflection is, so here for the omega 0,2, this is 0, the right-hand side. And otherwise, it's given by omegas of lower order, product of many of them, sum of all possible partitions and so on. So these are many terms. Suppose that's the case. So then we can prove that omega 0 m is always given by a universal formula of blob topological recursion now. So there's one piece which is exactly topological recursion. It's exactly the same recursion kernel of in our own term. And the remarkable thing, there's more. And this what is more can also be put into a almost identical recursion formula. So there's a new recursion formula which is extremely similar as that one. But you take then the residue at the reflected point, and so the anti-diagonal, if you wish. So otherwise, it's the same formula. So okay, this definition is equivalent or has the solution given here. And if we now take a very natural choice, namely the reflection is just z goes to minus z, and we take for x our r of z, which we found in the two-point function, then so these horrible equations, they, at least for genus 0, they are equivalent to that system and therefore have the solution given here. So this gives all our omega 0 n's. Well, by recursion, as usual. Okay. So one remark. Something will happen at higher genus. So that's what we work on. And the best strategy, maybe the only strategy, is what one should do is to prove so-called abstract loop equations. So they appeared here in this paper by long time ago, Borot, Wulkenhaar, and Pointin. So you consider, so there's a linear equation, consider your omega gns, distinguish one variable, and you sum over all points in the fiber of x. So over all these, I've wrote it here. The fiber of that consists of, in our case, d plus 1 points. One is this well, principal branch, if you like, and then there are d generically except of the ramification points, the other ones. And you sum over all these pre-images. Then the result should be something which is holomorphic at the ramification points of X or R in this case. And then there's a similar quadratic relation. So this sum is not restricted. You sum over all these omega GNs, all partitions of the genus and of the, well, the string of spectator variables. Get another, well, differential form actually, from omega 2, which is also required to be holomorphic at the ramification points. And these two conditions alone, the solution of these conditions is blob topological recursion. This is the result of Bourreau and Chardin. Whereas to get the true topological recursion, you need to do more. You have to specify other conditions, and they are not so natural. So the natural solution is blob topological recursion. So therefore, we have to prove this at higher genus 0, it's done. But we know, or we would like, or whatever, do more. Namely, we get more or less, or no. And then from this explicit formulae, we not only get the pole at the ramification points, but we get all poles. If you know F1, F2, we get all. And this is the way how you can also see that the second kernel appears. But now we are in a situation where we have more poles. So in general, we always have poles at these antidiagonals, but we have also poles at 0. At least conjecturally, that's all. Sure, it will be true. And we think we have the kernel at 0, but there's still some work to do. A lot of work, but okay, I hope.
So the first equation, so there is two abstract loop equations. First setting, first linear equation, if you divide by dx of z at j, then this one gives you just topological recursion, and f1 is 0 for stable.
Okay.
Yeah. So this is important that if you have not topological recursion, you have actually non-trivial f1.
Okay.
Topological recursion, you have f1 is something, is 0, and in block something.
Yeah, thanks. So yeah, in topological recursion, things simplify enormously. So here we have complicated right-hand sides, but we have them.
So you're saying quadratic.
No, this is in general, but this you have to prove. Yes, so you have to reformulate your Dirichlet equations, so this complicated system, into this form.
So if you have these two equations,
If they have proved it, then what's the point of thing?
No, this is a general thing. If you have these two equations, the linear one is the first, the quadratic one is the second.
Yeah.
Then the solution of this omegas is given by blob topological.
So it's
So if you have a model, you show that these equations are satisfied, and then you know that you have blob topological.
Is it if and only if, or
Yes.
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 if and only if?
Yes.
And if you have further conditions that your omegas have just poles at the ramification points, you have just topological.
It was a theorem by Bourreau.
No, this is proved here.
Bourreau and Chardin and this blob topological.
Necessary.
Yeah, this you have to do. So yeah, so we have to reformulate our three complicated equations into this form. We have to show that this reduces to that. Oh no, there's a lot of work to do. Okay, so I just flashed the outlook, and then okay, I'm happy I came through. So what should we do? Suppose everything is true, then we know also from Bourreau and Chardin that your omega gn encode intersection numbers on the moduli space of stable complex curves. So, okay, we would like to know which. Okay, but they're all the same, but there are rational factors in front of it, and just compare. And the question is, so it's a particular combination which is then encoded in omega GNs, and the question is, But that's a universal fact. You always have this. Question is this relation interesting or not? No one knows, but okay, something we would like to know. So there is a remarkable case where the relation is interesting. This is the ELSV formula, also related to Doris numbers. So, yeah, I'm almost at the end, but we have here the camera, right? Okay, it tries. Good. Yeah, my computer is old and unstable.
Maybe we can go with the camera.
Yeah, I'm almost finished, so it's not. So okay, yeah, okay, that's something we would like to do, and because this involution, which plays the key role in our formula, is so natural. Well, that's a hope that gets something interesting. And the second remark is in TR you always know that this relates to integrability. For block topological recursion, this seems, well, no, it's not known. And the question is there an integrable model behind? Would be fascinating, and it's widely open. I just want to say this, and I stop here, more or less, in time.
Okay, thank you very much. Thank you for a great series of lectures. Questions or comments? Maybe I ask one. So imagine all these homogeneous homogeneous, or how does it help
Yeah,
QFTs?
yeah.
It's not space is Q.
So okay, suppose we have all these. Okay, yeah. I taught you how to get the omegas. Then it is very easy to get from the omegas everything else. So all. Oh, no, this will not work. Let's browser. Okay, let's. So if we have the omegas, then everything else is relatively simple. It's just linear equation. There is an algorithm. You easily get everything else. So we get in particular this higher genus contribution to the two-point function. And then Alex showed you the formula yesterday. We get also basically all other higher cumulants. This step is easy. The hard thing is to get the omegas. So and then the question is, make sense of this here formal sum, but does it converge in sense of Borel that make n, the script n, a complex number, and your region is a circle tangent to the imaginary axis at 0. So prove that this can make sense. And then inside you get for n positive real number, it's the case what you want, then this sum, well, gives a well-defined function on the left-hand side. So this is the future, what one has to do. And then everything is understood.
So on an explicit form of this GN helps you.
Well, probably this is too much to hope, but it would be enough to prove that this can be done.
Relations to
well, you've seen here these catalyzed structures, and as I said, Alex found from these structures his relation between x and y, and there are relations.
This one relation Raimar showed is between z and minus z of the omega. It was in my talk somehow where I have this script GA1, smallest, the most simplest relation there, and probably if you would send all I'm not sure. If you would set all variables minus the variable,
Yeah,
this would
that's the
probably
other,
give the
yeah.
same relation as given in probability. Yes, I think this would.
Should be this.
Yeah. This, yeah, should give you the higher order moment equivalent formula. So it should be the same. Because here this sending z to minus z sends you x to y.
Yeah.
Because here is really the
X and Y are.
yeah, this gives you the reflection between x and y. This specific case.
Oh, okay. I see.
But it's more complicated in hedges. Okay, but anyway. Probably this would be the same.
Okay, well, I just added something by talk.
Okay, great.
Okay, are there questions in the Zoom? Okay, so it's no. Let's thank Raimar for great series of lectures. Coffee and cakes and fruits, and then come back at 30. Okay, very good. Thank you.